Welcome back. Srimad Swami Smarananda Maharaj, the revered president of Ramakrishna Math and Ramakrishna Mission, dedicated his life to spirituality and service. He passed away 26th March and he was my Gurudev. I have learned all my spirituality from my Gurudev. Actually, personal spiritual focus, self-discipline and self-esteem are known for positive growth in your life. So, since all I have learned from my Gurudev, so today's video I have dedicated to my Gurudev. Okay, let's start our actual video. We all of us know complex differentiability defined on a holomorphic function or analytic function, and a function be holomorphic or analytic when function is differentiable at every point z in gamma, where gamma be any set, and when function which are complex differentiable on whole complex plane, then we can tell this function be entire function. That means whole complex analysis actually depends on complex differentiability. So in my previous video I have defined what is the complex differentiability, what is the differentiability in multivariable calculus, because complex, F map from complex to complex, this means this is actually similar as F map to R2 to R2. That means we have to gain knowledge what is the differentiability in multivariable calculus, what is the differentiability in when function defined from Rm to Rn. We all of us know f is differentiable at a point A means there exists a Jacobian matrix A which is defined from Rm to Rn such that f of A plus A is minus f of A approximately equivalent to A is, where since this is the approximately equivalent to A is, so there exists one error E is, and E is equal to, that means f of A plus A is minus f of A minus A is, and this is belongs to obviously Rn, and as A tends to 0, this E is means this error always goes to 0. That means limit h tends to 0, norm of E is divided by norm is equal to 0, and f is differentiable at a point A means there exists a capital A which is defined from Rm to Rn such that limit h tends to 0, norm of f of A plus A is minus f of A minus A is divided by norm is equal to 0, where limit h tends to 0, norm of E is divided by norm is equal to 0. This is the differentiability in multivariable calculus, we all of us know, and this matrix is Jacobian matrix, and this differentiability is called as total differentiable, and this Jacobian matrix actually the derivative of this function when function defined from Rm to Rn. And in complex analysis, a function is differentiable at a point z0 means there exists a function f prime z0 belongs to complex number, and a function phi which is defined from complex number to complex number with the condition fz equal to fz naught plus f prime z naught z minus z0 plus phi z, where these phi z over z minus z0, as z tends to z0, this limiting value is equal to 0. Okay, this is the complex differentiable we all of us know, and by this theorem, since f is similar to complex differentiable in complex plane, means there exists differentiability f from R2 to R2. So complex differentiable at a point z0 where z0 equal to x0 plus I y0 belongs to C, means this is equivalent to f who is defined from R2 to R2 is actually the total differentiable at a point x0 y0, and the Jacobian matrix at x0 y0 has of the form A minus B BA. This is, I had seen in my previous video briefly. Today's goal of this lecture, today at first I will see mean value theorem, which is false in complex analysis. Then I will see differentiability we can evaluate by directional derivative and gradient. This is actually today's goal of this lecture. Now let's see our actual concept. At first I will define one function f which is defined from closed interval ab to complex number. This type of function is very interesting. This is actually the path. This type of function is actually like a path. Here function defined from interval to complex number. That means here the function is defined as ft equal to ut plus ivt, where obviously t map to ut comma vt, that means here t map to vector valued function, and this vector valued function actually the complex function, and obviously when f defined from closed interval ab to complex number means actually look like a particle along the path gamma, and the function is defined as gamma which is defined from closed interval ab to R2 such that gamma t equal to xt comma yt. That means when function defined from ab to complex number, that means this is actually the look like the particle along the path gamma, where gamma t equal to such type xt yt. Since here I have defined C, not R2, here I have defined C. Obviously C is same as the R2, but here the y-axis is the imaginary axis. So this is the vector valued function, but this is the complex function. So this is defined t goes to ut vt. I hope my all viewers have understood this is okay. And when function defined f of t equal to ut plus ivt, f is continuous at a point t naught, means if u and v each continuous at a point t naught, then we can tell f is continuous at a point t naught, because we all of us know when function defined from f Rn to Rm, then f equal to f1, f2 up to fm, where each fi map Rn to R, then f is continuous. We all of us know if each fi is continuous, and this concept here also used. F is continuous at a point t naught if each u and v are continuous at a point t naught. Here gamma defined closed interval 0 2 pi to complex number such that gamma t equal to e to the power it. We all of us know e to the power it means cos t plus I sin t. Then that means here t goes to cos t and t goes to sin t. Both as a continuous function. Gamma prime t means actually I to the power it because this is cos t plus I sin t. That means this is minus sin t plus I cos t. And this is actually I e to the power it. Therefore, gamma prime t equal to I e to the power it. I hope my all viewers have understood. Okay. We consider new function gamma who is defined from closed interval 0, 1 to complex number. And let ZW belongs to complex number. Then the line segment joining Z and W is gamma t equal to Z plus T W minus Z. And this gamma is actually the line segment joining Z and W. Then gamma t plus A is minus gamma t divided by A is equal to actually Z plus T plus A is times W minus Z minus Z minus T W minus Z divided by A, and this is equal to actually cancel this part, cancel this part, this part. This value would be A times W minus Z divided by A times W minus Z divided by A. This value would be W minus Z. So the line segment joining Z and W, which is actually gamma t equal to Z plus T W minus Z, this value is actually equal to W minus Z. So the derivative means gamma prime t is actually would be W minus Z. I hope my all viewers have understood. This is actually the line segment joining the point Z and W such that gamma t equal to Z plus T times W minus Z. Now I will say mean value theorem, which is false in complex analysis. What is the mean value theorem? We all of us know. In real analysis, if f is defined from closed interval AB to R, if f is continuous on closed interval AB, f is differentiable on open interval AB, then there exists a C in the interior point in a closed interval AB such that f b minus f of A equal to f prime C times b minus A. This is the mean value theorem we all of us know. But in complex analysis, consider one function f from 0 to pi to complex number. And the function is defined as ft equal to e to the power it, that means ft equal to cos t plus I sin t. Notice f0 equal to 0, f2 pi equal to also 0. Then f2 pi minus f of 0, which is equal to f prime c 0 minus 2 pi, this value would be 2 pi. And obviously, since f0 and f2 pi both equal to 0, this value would be 0 and this value 2 pi, and we all of us know mod f prime c, this value is always 1. So 0 equal to 2 pi, so 0 equal to 2 pi, this is not possible. So mean value theorem has broken here. So mean value theorem not applicable in complex analysis. Now I will see our next goal of this lecture. I will see what is the relation between differentiability gradient and directional derivative. This is our next goal of our lecture. I have seen few minutes ago. Let's see our next goal. If f is defined from Rn to R, then f is totally differentiable at a point A belongs to Rn, where obviously this A be a vector. Then the Jacobian matrix is del f del x1 at the point A, del f del x2 at the point A. Here obviously this type of A actually the vector del f del xn at the point A, and this is belongs to R1 plus n matrix. Then this Jacobian matrix at the point A, actually this is the gradient of this function at the point A, and this is just this type of column matrix 1 cross n matrix. Then f which is defined from U be the subset of Rn to Rm, f is differentiable at a point A means there exists a total derivative, and the derivative is look like d of fa at the point A acting on the vector A. Since here derivative from Rn to R, obviously A dot alpha, where these alpha be the gradient of this function at the point A. I hope my all viewers have understood this is clearly. Okay. That means gradient of f at the point A means actually the f prime A. Now consider a function f from Rn to R, f of xy equal to x square y. Then notice gradient of f xy would be, what is the gradient of f of xy? This would be 2xy x square. Then gradient of fxy at the point AB, this is equal to 2ab comma a square. Okay, this is actually the function which is defined from Rn to R, where f of xy equal to x square y. Then the derivative of the function acting on the vector AB is 2ab comma a square. I will see what is the directional derivative. F which is defined from U to R, where U be the subset of Rn, then f is differentiable at the point x belongs to U. For this, fix the vector v which belongs to Rn. Then f of x plus tv minus f of x equal to dfx tv plus error term, here considered error term is etv. Now divide the equation, both equation by t. Then this would be f of x plus tv minus fx over t equal to dfxv plus etv divided by t. And as t goes to 0, since etv divided by t, just multiply this part of norm v, and since I have multiplied norm v, so divide also norm v. As t goes to 0, this term goes to 0. Then f of x plus tv minus f of x over t, and limit t goes to 0, this value is dfxv. This is actually the rate of change of the function f at x in the direction v, and dvfx equal to actually dfxv. Okay, this is actually the directional derivative, and if f is differentiable, then obviously all directional derivative exist. That means when f is differentiable, since all directional derivative exist, that means dfxv acting on v is equal to dvfx, where v be the all direction of the function. Now I will see obviously one example. Consider a function f from R2 to R such that f of x comma y equal to x plus y when x not equal to 0 and y not equal to 0. And one otherwise, is the function be differentiable? Notice, just evaluate. Here we have to check differentiable at the point 0, 0. Is the function be differentiable at the point 0, 0? Just check the partial derivative. Partial derivative at the point 0, 0 always exists. But the directional derivative along the direction 1, 1, if we consider this direction, f of 0 equal to, by the definition, limit t goes to 0, f of, since x plus t, here v is 1, comma, y plus t minus f of x comma y divided by t. This is the definition, and here the point xy is 0. That means limit t goes to 0, f of t comma t minus f of 0, 0 divided by t. That means this is limit t goes to 0, f of t means 1 over t, and this value is actually infinity. So directional derivative does not exist here. Since directional derivative does not exist, so function not be differentiable at 0, 0. I hope my all viewers have understood this is okay. Oh well. But here at the point 0, 0 that partial derivative exists. That means partial derivative exists. That does not imply directional derivative exists. Okay. Now I will see the relation between gradient vector and directional derivative. We all of us know, if f defined from v to r be such that all partial derivative exist at x belongs to v, then we define the gradient, and gradient of fx equal to just partial derivative d1 fx comma d2 fx up to tn fx. And previously I have seen dv fx, directional derivative of the function fx along the direction v, which is actually equal to inner product of gradient fx with v. That means gradient fx, inner product gradient fx with v means gradient fx dotted v. This is the actual meaning. This is the actual direction derivative with respect to and gradient. That means directional derivative along the v of the function fx is equal to grad vector dotted with v, where v is the obviously unit vector. Now I will show one example. Directional derivative of the function fxy equal to x sin y, and the directional derivative at the point 1 pi in the direction of 3 minus 4, and this is obviously equal to gradient of the function at the point 1 comma pi dotted with the vector u. Here u is the in the direction of 3 comma minus 4. Then gradient fxy is actually sin y comma x cos y, and at the point 1 comma pi gradient of this function is the value is sin pi comma cos pi. This value is 0 comma minus 1. And here the v vector, here we have to find in this direction 3 comma minus 4. This is not the unit vector. So consider u with the unit vector of 3 comma minus 4, and this is actually equal to 3 over 5 minus 4 over 5. Then this is the unit vector of this vector v. Then the directional derivative of this function at the point 1 comma pi, this value would be gradient of the function at the point 1 comma pi dotted with the vector u, where u is the unit vector of this vector, and this value would be 4 over 5. That means directional derivative of the given function f in this direction would be 4 over 5. I hope my all viewers have understood easily. Okay? I will stop here. In my next video, I will discuss complex integration. Okay? But at first, I will highly recommend you, please see today's video with pay attention, because this type of concept actually very important for higher study. See you soon. Stay safe and stay positive always, and have a nice day. And since I have dedicated this video to my Gurudev, so pranam again my Gurudev. Okay? Thank you so much.